Over to you, Andy.
Okay. Let me also say, I know it's 6:30 over there and some people may be hungry, so feel free to eat your dinner while, no. Okay. So, I'm going to talk about work on flat space holography. Of course, there are different proposals for this. But I'm going to talk about the idea that that quantum gravity in asymptotically flat four space-time dimensions is dual to some kind of conformal field theory on a Euclidean two-sphere. And there's been a lot of different works in different directions on this subject, and I'm not going to review all of it. Mostly well, the first half, I guess, will be some review of parts of it. Mostly I'm going to talk about the stuff I've been doing. And there's a recent paper which appeared with Monica Pate, a junior fellow, Anna Riclario, there's no S on the end of her name, who's now just starting a postdoc at Perimeter, and LSUN, who you all know. And then also soft S matrix and gravity with Mina Himwich, Shruti Narayanan, Monica Pate, Nisarga Paul, and then a soon to appear paper with Nimar Khani Hamed, Pate, Riclario, and myself. And then one that is in progress and I probably shouldn't be talking about, but it's fun and relevant, and just because it's a little too early. But I'm going to talk some about that with Alex Atansov, Melton Walker, and Anna Riclario. So what is the basic idea of this approach to flat space holography? It's basically that you think of the S matrix, which we take to be the basic set of observables in four-dimensional asymptotically flat quantum gravity, is dual to a conformal field theory on the celestial sphere. And the idea is that you take a sphere, it's the Euclidean sphere that lives at null infinity, and you put various operator insertions in the sphere, and think of this S matrix as a correlator. And the operators are inserted according to the angle at which they came in or out of null infinity, and they have various quantum numbers, which at the starting point would be the energy, the charge, so on. You can tell whether it's an in or out operator depending on whether the energy is positive or negative, and spin, and so on. But the advantage of doing this is that, or one advantage of doing this is that the Lorentz group, which is SL2C, is also the global conformal group of the sphere. And therefore, this collection of objects over here is transforms like under the global conformal group, like a conformal field theory. And therefore, it's not natural to characterize the operators by their energy momentum. It's better to characterize them by their representations under this global conformal group. In other words, we put conformal invariance first rather than translation invariance first. And translational invariance will reappear in an extremely subtle and interesting way, but everything will be manifestly conformal invariance at every step. Now, the important thing that made this really interesting to do is that Freddie Cacciazzo and I a few years ago proved a soft theorem which was equivalent to the statement that in quantum gravity, not quite in quantum field theory, but in quantum gravity, this set of quantities actually has to transform not just over the global conformal group, but over the full infinite dimensional conformal group that we're used to. So one may hope that some of the powerful techniques that we have in two-dimensional conformal field theory can be applied to one of the most interesting parts of the real world, which is quantum gravity and the approximation that the universe is flat, which is a pretty good approximation. Okay, it's editing, not, why is it doing that? Okay, so the fact that you can do this rewriting is a tautology. It's just a change of variables. So far, it's not, there's no assumption in the statement that you can rewrite the S matrix in that way. The question is whether it's a useful thing to do and whether you can get new insights by doing so. And I'll try to argue in this talk that the answer is yes. Now, the first step in finding a holographic dual is, in ADS-CFT, the first thing that was done was the near horizon symmetries of black holes in various dimensions, and the near horizon regions being where they become anti-de Sitter space, were matched to symmetries, conformal symmetries of various field theories. That's the zeroth order test of a holographic duality. Both sides had better obey the same symmetry. Now, that is a step which we've taken there's been a lot of progress in the last few years. In particular, understanding, first of all, what BMS symmetry is, how it acts in 4 dimensions, what its extensions are, and there's actually much more to learn than you would think. There are infinitely many symmetries, and we don't understand how they're all going to act on this conformal field theory on the celestial sphere. And I think there's always been a feeling in our community that BMS group was important. In fact, I'm remembering now the first person who started mumbling about it, I think, was Rajesh when he was my postdoc. He probably remembers that he had a little project. I don't think it read. Isn't that right, Rajesh?
Yeah, I remember that. Yeah, it didn't go very far at the time.
1998, Rajesh kept coming into my office and saying, BMS group, it's got to be really important. What are we going to do with it? What are we going to do with it? and anyway, that stuck in there, and it took a long time to put it all. It took a long time to start to find the techniques to put it together, and there was a very important group, a very important paper, very prescient paper, which nobody really paid attention to by De Boer and Saludkin in around 2001. And they said, hey, we understand anti-de Sitter space really well. Let's just think of flat Minkowski space as a kind of non-compact compactification, where the internal over A. And this is how you do it. You write ADS with the hyperbolic slicings. This is Euclidean ADS. This is DS3, which has the same isometry group. And then you regard this direction, that the direction that parametrizes these slices, is kind of an internal dimension. And since it's a non-compact internal dimensions, the so-called Kaluza-Klein modes will have a continuous variable rather than a discrete variable. And therefore, we would expect some kind of continuum of operators. And they worked out the mathematics of this. And then they said, since these are anti-de Sitter space slices, there's a boundary here. The boundary of them, the sphere, is the celestial sphere. We should get some kind of infinite dimensional conformal group acting on this. Now they looked at this and they saw there were two spheres. So they thought there would be two conformal groups. And they were thinking of a map between in correlators and out correlators in two different conformal field theories. Recently, we've understood that these conformal groups are locked by boundary conditions at infinity. So the whole thing, so it's a much nicer picture. The whole thing is just one, so there's one celestial sphere because the boundary conditions at null infinity give a locking between this conformal group. And the whole thing can be regarded as a correlation function on one sphere, which we're much more familiar with. Okay, so why is this? There's all kinds of reasons that I've been interested in why this is a fruitful venture. One is that you are, we all love and by now know well the ADS-CFT correspondence, but we don't think that the holographic nature of quantum gravity should be confined just to anti-de Sitter space. And so probably the next step, the next easiest thing is probably going to be flat space. The real universe, which is probably asymptotically de Sitter, that's probably one yet more difficult to understand. One of the things that's been uncovered in this enterprise is that there are an infinite number of symmetries and conservation laws. It's akin to ADS-CFT in 3 dimensions, but even more so. There's so many symmetries that we haven't even classified them yet. We'll talk a little bit about that more later. And these will greatly constrain how information can flow in and out of a black hole. It'll constrain the soft and the hard modes that go in and out of a black hole. And so that could be related to black hole information. And we need to understand how these symmetries are implemented in a concrete way. And that's what we're doing here. There's also been a growing chorus of which one of the most powerful entries was a recent paper out of your group of trying to understand what the most general graviton 4-point scattering amplitude is. It seems to be subject to an impossibly large number of constraints. And in this talk, we're going to add a lot more. And so it seems to be, within the realm of possibility that, in the next decade, we will find some expression which would be the most general consistent form for the 4-graviton scattering amplitude. In the process of this, we're going to connect to many of the ideas that have come up in the Bootstrap program and new ideas in 2-dimensional conformal field theory have been echoing with this approach. Also, it's bottom up. In this enterprise, everything I'm going to talk about today is relevant, is a feature of the real world, not assuming string theory at all. We're making, we're describing things about what goes on in the real world around us, and our improved understanding of these symmetries has not just led to new ways of understanding old effects, but there's actually been predictions for new memory effects, which have been proposed to be seen at LIGO. In gravity, new kinds of memory effects, which are related to these symmetries, are going to be measured at this $1 billion electron-allion collider, which was just improved. We'd like to find things for Lisa. We'd like to find things for at the LHC. So there's some interesting, novel, experimental aspects of this program also. But we're also very much using the insights that we've had. So I'm having a little trouble with, okay. Now, as I said, this is a bottom-up approach. The bulk side is defining the boundary side so far. So just to understand what that means, we can imagine an alternate universe in which Brown and Hanot had done their work on ADS3 and found the conformal symmetry, and before Vafa and I found the conformal field theory dual of the black hole, or before the Maldaceno found the general dual for anti-de Sitter spaces. And even without those things that came out of string theory, we could have gone a long way. String theory kind of gave us a shortcut, but we could have, somebody might have suspected that from the asymptotic symmetry analysis of Brown and Hanot that quantum gravity in ADS3 was dual to a two-dimensional conformal field theory. You could have then analyzed, you could have learned about locality, you could have learned a lot. And in fact, this program has kind of been returned to in this recent work with replica wormholes and so on, where people are trying to understand, use the insights we got from quantum gravity to have a bottom-up approach where you're not assuming any microscopics. But the top-down approach is also important. And I think it's entirely possible here that in string theory, where we have a quantum gravity, that theory of gravity that we understand microscopically, that we could derive what the holographically dual two-dimensional conformal field theory is. And indeed, Stieberger and Taylor found some hints that, of course, we already know an example where the four-dimensional S matrix is computed by a correlation function on the sphere. It's called string theory. Conformal field theory on the sphere, it's called string theory. And, but the relationship between that worldsheet CFT and this celestial CFT isn't completely clear. And what's not clear at all, but Stieberger and Taylor found some connections. But this isn't an easy problem. An intrinsic construction of a celestial conformal field theory, which of course we need ultimately to have a complete example of a holographic duality. So you have two sides you can compare, not just one side, which you construct from the other side. That would be like a major breakthrough. But I want to say that even without an intrinsic construction along the way, though we're just using low energy reasoning and symmetry, we're seeing a lot of things that look like strings. Now, when we try to go from flat space ADS holography to flat space holography, a lot of things are different. So for example, in ADS holography, the Hilbert space of the holographic dual is the Hilbert space of the bulk theory. They're just equal. And here it's different because the holographic theory is Euclidean. It does have a Hilbert space that you can get by the state operator correspondence. And that Hilbert space is related in a very complicated way. It kind of contains the same information, but repackaged as the whole Hilbert's in a way we haven't fully sorted out from the bulk Hilbert space. And celestial conformal field theories aren't conformal field theories. They're not garden variety conformal field theories. They have funny, their weights tend to lie, well, I'll talk about that in a minute, but they don't have the same kinds of positivity constraints, and different things happen. They're different. Here's a discussion. Well, they both conformal field theory because they both have the conformal group. They have current algebras associated with gauge symmetries. In usual conformal field theory, we like to talk about OPEs. We're going to come to that later. Here we're talking about actually collinear singularities has been a major topic of discussion in quantum field theory for many decades. And under this map, that maps into the study of OPE singularities. Biggest difference here is the different kinds of representations. And also in the celestial conformal field theories, beyond the usual infinite dimensional Virasoro action, there are an infinite number of new symmetries related to the other soft theorems. And, you know, conformal field theories are very constrained generally. And it didn't seem like there would be room for a conformal field theory to have infinitely many more symmetries and not just be a free field theory, but we have examples of them. And these symmetries act in ways which are very different from what we're used to. And that's what we're really trying to understand in a concrete way. So there's a very beautiful structure that is coming out, but it's sort of, yeah.
On the previous slide, you had single valued for the CCFTs. What do you mean by that?
Well, I just mean, yeah, locality. So I'm going to talk about locality. There are different notions of locality that people have in variety conformal field theories. And one is simply that if you take two operators around each other, you come back to where you started. And that is true in the ordinary, in the celestial conformal field theories. That's just saying if you consider the S matrix and you move one of the asymptotic particles around the other one, you'll come back to the same S matrix element. Another kind of locality that I think we've made some progress on understanding is these, and I'm going to have a transparency on this, these conformal field theories have singularities when celestial conformal field theories have singularities which one can see delta function singularities in the 4-point function, only in the 4-point function, not in the function, or higher, which are forced on one by translation invariance. And we can see that that can happen in an ordinary conformal field theory, and we'll see that that is the origin here, that there are an infinite number of primaries, and each primary contributes something finite, but you have an infinite sort of correlated sum, which is correlated because of the translation symmetry, and it's that infinite sum that's giving the delta function. And actually it's very similar and maybe the same thing as these bulk point singularities in maybe closely related to these bulk point singularities in Lorentzian conformal field theories. Okay, so I'm not going to present a grand vision of, and please interrupt with questions. I've given seminars many times at TIFR, and this is my world record by a factor of 10 for how long I've been able to speak without being interrupted.
Andy, you...
I wasn't including Shiraz in that statement. No. No kidding.
Excellent. So this S matrix here is the space-time S matrix going to be related to the partition function of your conformal field theory is a function of sources as it is in ordinary area CFT? The thing that obeys SS dagger equals 1, is that the world sheet, is that the two-dimensional boundary partition function as a function of sources?
No. Well, well, okay, so that's not the way we said it. We said we have an S matrix, and you can think of the S matrix as an object associated with a bunch of points on the celestial sphere. And so with each of those points, we just define the operator to be whatever it would be, whatever the properties it had. So it had the right symmetries and so on that it has in the scattering problem. And then we just call whatever the S matrix is, the correlation function associated with those points. Now, the sources and operators are related by this shadow operation, which changes dimensions from 2 to d-2. And so this question that you're asking becomes much more subtle, because we'll see that it's a two-dimensional conformal field theory, and the dimensions tend to be on the unitary principal series, which is 1 plus I lambda. So what's a shadow and what isn't doesn't have an a priori distinction. It's like in that, I mean, there are lots of examples, but I guess the first one was discussed by Klebanoff and Witten, where you have operators in a gap and you can't canonically say what's the shadow and what's the operator and what's the source. And that also, that distinction is also related to the fact that, we have a Hilbert space. The Hilbert spaces are identified and in ordinary ADS-CFT, and we can usually cleanly talk about what the coupling constants are in the CFT and what the states are in the CFT. And varying one corresponds to varying the source, and varying the other one corresponds to varying the state. Here, we have to make some division, and what's been done so far is just arbitrary divisions. I'm going to call this the source, and that is indeed a subject which we're very much wrestling with, what the consistent dictionary is there, and what the and is there more than one?
Thanks a lot. One more quick question. When you say SS dagger is equal to 1, now in 4 dimensions, I believe S matrices have infrared divergences associated with the graviton. So is there a finite S matrix that also obeys SS dagger equals 1?
Yeah, so that is a very important question, and one that I think, though it's new, I think we've made some very exciting progress on. I'm going to quote the result. It's in this forthcoming paper with Nima and Anna and Monica. But already several years ago, this whole subject was sort of, had better have told us something interesting about infrared divergences, because we're talking about the soft structure. And indeed, it did tell us something about infrared divergences. And this is a different talk I was giving. It's now an idea which has been developed, and there's been some proofs and generalizations by Churi and Kuo and some other people, that very simple interpretation in this framework of what an inservation infrared divergence is. And that is, this is taking me a little bit aside, but it's a really important aside. That is, there are conservation laws, and if you violate the conservation law, the amplitude better be 0, and there are infinitely many of them. And every process every exclusive process with a finite number of particles, in particular a finite number of soft particles, will violate this conservation law. And that's why they're infrared divergences. They exponentiate and set the amplitude to 0. So if you only analyze amplitudes that obey the conservation laws, you never get any infrared divergences. And this was said, though there was some mistakes in that paper and some mistakes in the literature, which we cleaned up. This was said, 50 years ago by Chung and Kulish and Fedea. But now we understand what their construction means. So, okay, but there was still a question of this Fedea-Kulish basis, but now we've seen that something beautiful happens when you go into the conformal basis with the infrared divergences. And I'll have a couple transparencies on that later.
Andy, can I ask a question, please? Is it okay?
Yes. Yeah.
Okay. So your framework looks very four-dimensional. So suppose I go to 5-dimensional gravity, then I suppose I will be discussing a higher celestial sphere there. And is there any thoughts about that, or this is very four-dimensional construction?
Well, yeah, there are quite a few papers. There are quite a few papers on generalizing all of this to higher dimensions. I was myself exiled from 4 dimensions for many decades, and so I'm happy to just talk about the 4-dimensional case like I'm doing here. And it does turn out that 4 dimensions is kind of the critical dimension for this story, in the same sense that 3 dimensions is the critical dimension for ADS. There's much more we can say about ADS3 CFT than any other CFT. I guess there are special things for ADS5 because we know so much about n equals 4, but the appearance of this infinite dimensional symmetry group has been an incredibly powerful tool for ADS3. And so this flat space holography in 4 dimensions seems to be the most interesting case. I've written maybe 2 or 3 papers on the higher dimensional case, but there are a lot of them. And one of the features is you always have a conformal field theory on a sphere. And the reason you get that is that when you want to define the sphere at null infinity, there's no meaning in quantum gravity and general relativity to taking the sphere out to infinity in a uniform way. You can push the sphere up to null infinity at different rates in different directions. And in a curved space-time, there's no meaning to say you're taking it rigidly out to infinity. So the only structure that could exist on that sphere would be a conformal field theory. So it's always a conformal field theory, but what kind of structures, it's a very interesting subject to explore, and it's probably good to be exploring them all at once, because some things that you may think are general aren't, and certainly in string theory, that's how it worked. In fact, I historically got burnt because when I was trying to understand duality in string theory, I thought, why should we think about anything but 10 dimensions? And 10 dimensions turned out to be a very hard place to think about duality in string theory. It was much more transparent when you talked about 4 and then work your way back up. So we should certainly be thinking about all of this. Okay, so here is this is mostly in this beautiful by Pastersky and Shao. Well, not this part, but so what is a conformal basis amplitude? So if we take an ordinary scattering amplitude, and I guess I didn't write this on this transparency. Let me write it on my blackboard. What you do is you have a vector P mu, and I might not be getting this exactly right, we'll talk about null vectors. I guess it's 1 plus ZZ bar, Z plus C bar, I Z minus C bar, 1 minus ZZ bar. Okay, this is in every paper on the subject. In other words, you can trade a null vector P for its energy omega and its position Z, which is a coordinate on the celestial sphere. So we can also write this Z as equal to P1 plus IP2 over P3 minus P0. Okay, so I hope you can sort of see that. And that's P. So here, if you take an ordinary momentum space scattering amplitude and you do a Mellin transform, you get something which transforms under the, it's an object which lives on the sphere. It's labeled by things which are at points, and they're labeled by things like their conformal weight, lambda 1, which is really the boost weight. The conformal weight is the boost weight. It's the Rindler energy. It's the eigenvalue under L0. And it turns out that these are primaries. They're annihilated by L1. And what Pastersky and Schaus showed is that if, let's just talk about a scalar. If you let the H, you have H and H bar, L0 and L0 bar. If you let H run over the imaginary axis shifted by 1/2, you get a complete basis of all normalizable wave functions. Now, that turns out to be a tricky thing, because if you have a normalizable wave function, say in momentum space, and you act on it enough times with the Hamiltonian, you'll get powers of omega, and it won't be normalizable anymore. And so if you want to talk about representations of the Poincare group, the normalizable states are not enough. That is something we have to understand. But anyway, this is how you construct, this is what we call a celestial amplitude, and you construct it for massless particles by a simple Mellin transform. For a massive particle, they are characterized by points on the hyperbola, p squared equals m squared, and we have to do a bulk to boundary propagator on that hyperbola to construct the conformal basis operators. So these scattering amplitudes in a conformal basis have been computed in quite a few examples now. The one thing I want to emphasize here, though, is that you can get ultraviolet divergences already at tree level, because these conformal basis amplitudes involve integrals over energies. So there's no such thing as the conformal basis amplitude for Einstein gravity. It just diverges if you're on the unitary principal series. And there is for string theory, and it's been computed. Even in Yang-Mills theory, a scale invariant theory, it turns out it's only marginally convergent. And so you have to regulate, put in some UV regulator. You can take it to 0, but it's a little tricky. So this whole story really wants to be discussing things which are very soft in the ultraviolet. You don't have the freedom, it's kind of baked in. You don't have the freedom to discuss theories which are badly behaved in the ultraviolet, because you will run into trouble already at tree level. And so that's a nice thing, because in I think in many other approaches to, like, for example, understanding what the general for graviton scattering amplitude is, you don't have any natural way of putting in the constraint of good UV behavior. Now, of course, we're no longer talking about energies, so we no longer have soft particles, but we have conformally soft particles. And where you can have particles where H and H bar become an integer and 0, or you can have a current 1, 0. That's the current whose Ward identity is the conformal basis analog of Weinberg's soft photon theorem. And also there's a 2, 0 operator using the graviton, and that's the one that gives us the stress tensor. Okay, now something happens that really is unfamiliar from ordinary conformal field theory. Sorry, one more thing I wanted to say back here is we're given the particle content. And once you know the asymptotic free particle content, you know the spectrum, not the density of states, but you know the spectrum of the conformal field theory. It's a continuous spectrum. And so it's a different kind of problem. Usually in a conformal field theory, finding the spectrum is very difficult. Here you have it, not that this is an easier problem, but here it's arranged differently. You start out knowing what the spectrum is. You have a continuum for every particle in the theory. Now, super translations are more subtle. So for gravity, it turns out that the series, because of the spin, you want H minus H bar to be equals to 2, and you want H plus H bar to be equals to 1 plus I lambda. So a graviton, a physical graviton, would have conformal weights that look like this. This is the unitary principal series for spinning things. And the soft graviton that is related to super translations has these weights, but acting with a translation in momentum space multiplies by omega. But multiplying by omega, if we go here, if you multiply something by omega, it's equivalent to changing H. So this is an operator, a very interesting operator associated to super translations, which has, it's meromorphic, but it shifts the conformal weight by a half, the left and right conformal weights by a half. So you have a symmetry in the theory, translation invariance, which in the usual approach acts in the most trivial possible way, just multiplies things by phases. But in this theory, it maps one operator, in this basis, in basis of boost eigenstates, it maps things of one conformal weight to a thing of another conformal weight. And this, of course, would only be possible if all operators lied in continuum, as they do, for example, in Liouville theory. And it's hard to understand how the correlation functions could have this symmetry. It seems like too much for a set of correlation functions, for all of them to be related by shifts in the conformal weights.
Sorry, Andy, one question.
Yeah.
This HH bar that you wrote for graviton,
yeah.
Is it not that the H has plus I lambda and the H bar has minus I lambda?
No.
I see.
They're not complex. Okay, yeah. Very good question. So L naught and L naught bar are elements of SL2C, right? So SLT has 6 generators, L plus or minus 1, L naught, L bar plus or minus 1, L naught bar. If you realize these in vectors on on Minkowski space, they don't obey the usual hermeticity, and they don't. The Klein-Gordon, there's two inner products. There's the Klein-Gordon inner product, which is unitary, and then there's the conformal field theory inner product. So the Klein-Gordon inner product is unitary in the sense that all modes have positive norm, but then there's a conformal field theory inner product in which L1 dagger is L minus 1 rather than L bar 1. So these things are acting a little differently, and L naught plus L naught bar is the boost weight. And so we see here that the boost weight here is 1 plus I lambda. And if you work it out, actually, L naught plus L naught bar is I times what we would call the Rindler energy. And so the fact that L naught plus L naught bar has an I lambda in it means that there's a real part of the Rindler energy. And from that point of view, the puzzling part is that the Rindler energy also has an imaginary piece, as you would if you take the derivative of a Rindler mode, that will have that will give you something with an imaginary piece. So yeah, so that's definitely plus I lambda, and yeah.
Thank you.
Now, at the end of the day, I think we're going to be implicitly analytically continuing things as is often done, and make H and H bar independent, which is tantamount to going to 2-2 signature. Okay. In fact, we're kind of doing that here because we are expanding, as people do in the amplitudes discussion. We're going to expand in Z1 minus Z2 and not Z bar 1 minus Z bar 2. So, okay. So now, just to show you how powerful translation invariance, how powerful these symmetries are, I'm writing the OPE of two gluons. Now, an OPE of two gluons, it's what happens when they get close to each other, but a quantum field theorist would call it a collinear singularity. And if you translate into this language of the celestial sphere, the standard form of the collinear singularity between two gluons turns into a 1 over Z1, between two positive helicity gluons, turns into a 1 over Z minus 1 minus Z2 on the celestial sphere. So just from dimensional analysis, from the scaling weights here, we learn, so if H1 is on the principal series, H2 is on the principal series, H1 plus H2 minus 1 is also on the principal series. And to make the dimensions add up, we need a 1 over Z1 minus Z2. And now I'm assuming that the OPE coefficient is an arbitrary function of the only thing which is labeling these two operators, H1 and H2. But now we can act with translation invariance on both sides of this operator, of this equation, and we get three terms. We get one that acts here, one that acts here, and one that acts here. And it gives us this cool recursion relationship between the OPE coefficient. But that's not all. Well, I've already used part of the leading soft symmetry and saying that we need an FABC, the structure constant of Yang-Mills here. That's just global color symmetry. But there's a further constraint from subleading soft symmetry. So there's a symmetry, large gauge symmetry, associated with the leading soft gluon symmetry. And the subleading soft gluon symmetry, we're talking about tree level here, or an effective theory, it takes a very different form, gives us another recursion relationship. We can act with it on both sides, and we get a relationship like this. Now, along with some boundary conditions at infinity, these two recursion relations famously fix this function to be their beta function, product of two gamma functions. And in fact, in a rather tedious calculation, this had already been calculated by Fan, Fotopoulos, and Taylor by taking work on collinear singularities in Yang-Mills theory and doing its Mellin transform. So just these simple symmetry arguments determine the leading singularity, and in fact, it determines all the leading singularities. This is a page from our paper between gravitons and gluons. And one of the things that's very interesting here, which I can't resist mentioning, is that the subleading soft symmetry is corrected by a finite number of operators of the right dimension. And in fact, it does get corrected when you couple to gravity, because there's a coupling between the graviton and the stress tensor of the Yang-Mills theory. And that means that the subleading soft symmetry has a term which mixes up gravitons and gluons, changes gravitons to gluons and vice versa. And so we get a mixture between the OPEs. We can learn about the mixed OPEs as well as the single OPEs. And so we fixed them all by symmetry. They hadn't all been computed using Feynman diagrams, but we computed and they compared, and everything agreed at the leading order. And this and still we haven't even used all the symmetries. We haven't used, for example, the subleading. We haven't used all the symmetries in this discussion. And this is telling us that we don't know exactly how far this will go, but this is telling us that these symmetries are useful. We can learn things from them. And it's telling us something about scattering amplitudes that we weren't able to, well, this is these now, I'm about to talk about scattering amplitudes that we couldn't get at. Okay, so we talked about 2-point functions, that's just the free theory. And we talked about the OPEs, the 3-point functions. We're talking mostly about massless particles here, so the 3-point scattering is degenerate. But now let's talk about the simplest case of a scattering amplitude, which is the 4-point scattering amplitude of a massive and a massless scalar. We're scattering 4 massless scalars with a massive one in between. This turns out, yes.
Sorry, a question. So just for the 2-point function in conformal field theory, we know that the 2-point function has support when the two operators in question are either have identical scaling dimension or have dimensions related to each other by the shadow transform. In the former case, it would go like a power law, and the latter case, it would go like a delta function.
Yes.
So is it the latter case that is being realized here? And what happens if, how to rule out this possibility when you have insertions of the two same operators, and which conformal field theory the conformal symmetry then will tell us that it should have a power law.
Well, okay, so so that's a very important question, and one that we've thought about and don't have a complete answer to, but and already discussed in Pistersky and Shao. So, there are many different cases here. So it depends on what basis you use. So if you find, so in some bases, and in the most common basis used, I think it's what you were calling the latter case, where it's a delta function. But if you have two things which are a delta function, if A and B are a delta function, then A with the shadow of B, which reverses lambda, becomes a power law. So for massive particles, for example, their self-shadow, that is, positive lambda is the shadow of a positive lambda thing is a negative lambda thing. And so you can find a basis in which you get the power law. And similarly, for massless particles, you can also find a basis in which you get the power law. So the answer to that depends on how you're setting up the theory and how you're choosing your basis. And we've mostly been working in a basis where it's a delta function. But I think it's a nicer thing to do to work in a basis where it's a power law. And we're trying to understand.
Is there a four-dimensional meaning to the case when the two-point function is a power law?
Well, it would just be a well, if you take something and you take its shadow, you know, if you have something that comes out at a point Z and you take its shadow, it will, the inner product of those two states will have a power law. I'm not sure what you mean by interpretation.
I mean, I had in mind that when you have a delta function, it in four-dimensional, the four-dimensional interpretation is that a particle just propagates freely. Yeah. While if you were to have this shadow basis for one of those, in which case you will get a power law, would there be a four-dimensional interpretation, a natural interpretation? Maybe because the shadow transform involves some sort of a integration on a non-local operation.
Right. You might be wanting to use a different basis for your out states than your in states. In order to get that, as you say, right, that's why we've been using the delta function. Okay. Because that says that an in thing goes to an out thing. But you can use another basis where you get a power law, and that basis, such a basis might be useful in getting less singular representation, less singular representations and relating more to properties of two-dimensional conformal field theory.
Okay, thank you.
But it's a really important question.
I have a question.
Yeah. You know, it's a little easier to answer a question if I can see the face.
Right. Can you see me?
Yeah.
So could it be that when you can treat the gravity semi-classically in the bulk, and then say gravity is semi-classical, you are computing the S matrix, but now you demand that S matrix, that the one that is computed, satisfies the word identities of the CFT. More specifically, let's say the commutator of two currents. the fact that commuted or the OPU of two currents has to be satisfied by and has to be of the same form as the one that you mentioned, let's say, like the current algebra, that might constrain the UV behavior of the bulk theory. Could it be?
Well, I think if you're just talking about the leading currents, I don't think so, because, well, it might. I'm going to say more, or I'm going to talk more about the UV behavior and how it enters into that story. And that's kind of the subject of the paper with Nima and Monica, what UV has to say about this. And we have only some preliminary observations, but maybe you could ask me your question again in maybe 4 slides.
Okay, thank you.
Okay, so the simplest case is 4 scalars and a 4-point function of scalars. That's the simplest 4-point scattering. The other ones are really qualitatively similar. We've done, 4 gluons, even 4 gravitons in string theory. Stieberger and Taylor did that. But they're all kind of qualitatively similar. Now, one thing, I'm not going to explain this. So the amplitude a priori depends on the 4 positions of the celestial sphere and their 4 conformal weights, which would be 1 plus I lambda k. But it turns out that translation invariance tells you that it can be written as a prefactor, a kinematic prefactor, which appears in many papers. I'm not going to write it out. And then it's a function only of the sum of conformal weights. I've written in here. It's a sum just of this quantity beta, which is the sum of all 4 conformal weights. Now, in ordinary conformal, this sounds crazy. You wouldn't think there would be a conformal field theory with that property because typically they depended in a detailed way on the individual conformal the correlation function would depend on the individual conformal weights, but here it just depends on the sum. So this is the answer if you do the Mellon transform. And one of the things I want to, and let me just say here, Z, Ij is the difference between the Z's, and the conformal cross ratio under the holographic map, the conformal cross ratio of the 4 points, the conformally invariant cross ratio of the 4 points, which is Lorentz invariant, SL2C invariant, maps in to the ratio T over S of the space-time Mandelstam invariance. So the Reggie expansion is the same thing as the expansion in the cross ratio in the conformal field theory. Now, and then it depends only on the conformal weight beta. And then there's this delta function which restricts the cross ratio to be real. Now, that looks very, very funny from the point of view of conformal field theory. But it's very simple. It's true for every 4-point amplitude. And it's a very simple thing because if you, suppose you have a 4-point scattering and we look now at the first 3 particles, well, you can always find a circle through 3 particles, which we can think of as the equator of the celestial sphere. And now if you've got 3 particles lying on the equator, by momentum conservation, space-time momentum conservation, which is completely obscure in the conformal basis, the 4th point better lie on the same sphere. And if the 4 particles on a sphere, 4 points on a sphere, their conformal cross ratio is real. So, so you always get this delta function, which follows in a very simple way from translation variance. At the same time, this obeys all the properties of a conformal amplitude. Well, there are various kinds of positivity properties it doesn't obey, but it's conformally invariant. And we would expect to be able to expand it, expand it conformal blocks times square of operator product coefficients in something that looks like this. Now, already this is very strange. In field theory, we have to sum over exchanges in different channels. One of the amazing things in fundamental string theory was we could expand and sum channel just in one channel, just in the T channel, or just in the S channel, and get a convergent expansion for the whole amplitude. Now, here, we see that we can make that conclusion that there is such an expansion just by looking at the conformal properties carefully. And so the fact that you can write this sum over Feynman diagrams in this way, just from symmetries, is strongly reminiscent of string theory and gives me some hope that this program, which many others have been advocating, of pushing the general 4-point scattering amplitude into stringy form without using string theory, as of course, I'm not sure you said it in that paper, but it was clearly one of your motivations on your 4-point amplitude might work. So, okay, how does this all work, and how on earth can we get a delta function? Okay, so the operator product expansion, again, you can use translation invariance, though Shao and Lamb computed it directly from a Mellon transform. The operator product expansion is again an Euler beta function with these arguments. That's for something with weight lambda 1, lambda 2 on the unitary principal series, going to something of weight n, where n is a real integer conformal weight on the positive real axis, given by this. Now, we did it for general couplings, but I'm just going to write down the answer here in the limit where all those diagrams fix to a point. And you can do the partial wave expansion to form the contours, and you get this expression, which beautifully has the product of the OPE sitting in front of there and a discrete sum over the weights. And so, okay, it's a very pretty formula. We don't fully understand the physical interpretation of it. We're very interested in input on that. So we have the product of the conformal weights. So we have the transferred states, the conformal blocks, all have integer weights. These are conformal blocks for integer series. So we have the product of the OPEs here. We have the I4. And then we have these two funny things, cosecant beta and this product of cosines. Exactly these things appear in formulas we don't fully understand by Simmons and Duffins and Karen Huo. Maybe we want to absorb those into the analytic continuation of these conformal blocks here. I'm not sure. We're working on trying to understand these. So we have a continuous series with real positive conformal weights. And then we have, a discrete series with real positive conformal weights. And then we have a continuous series of things that are light ray transform operators. And they appear in just, again, just like formulas that these people have been writing down. You have these light ray transform operators, which appear in Lenzer and CFTs, and indeed were implicitly in 2-2 signature because we're treating H and H bar independent in our expansion. And they are also appearing here. So it's looked kind of like the complete set of states you need for the 4-point function can be viewed as these things with real positive conformal weights plus some light ray transforms. There's a longer formula for finite M. Now, here's the beautiful thing. This formula, every term in it is, or one of the beautiful things, every term in it, of course, is non-singular for any finite value of the cross ratio Z. We have to have an infinite number of terms because we have to form a representation of a translation group, which shifts these n by integers. And that ties together this whole structure. And you can explicitly check that while these two terms are separately non-zero for any z, when z and z bar are not equal, they exactly cancel. But when z and z bar are equal, they give you this delta function. So the delta function is coming. It's not that the theory is, it's not because the conformal field theory is non-local, it's because there are an infinite many of primaries, and because all their interactions are related by a symmetry, translation symmetry, they can combine to do something special, and what they do is what they must do is produce the delta function, which was promised to us by translation invariance. Okay.
Sorry, Andy, one question.
Yes.
In the previous slide, this case that you have written, they are the 2f1 hypergeometric functions, which are the conform blocks that appear for the global conform group.
Yeah, they're SL2C conformal blocks. Yeah, they're the standard hypergeometric functions, and they also depend on the H12s, which are proportional lambda3 minus lambda1.
And the Virasoro symmetry hasn't yet been used here.
The what?
The Virasoro.
No. And this thing, amazingly, of course, has to realize, my understanding is that these sums over conformal blocks, the individual terms don't have Virasoro symmetries, but the sums do in some miraculous way.
Mm.
And this one, not only do the sums have the Virasoro symmetry, but they have the translation symmetry, not to mention the subleading, well, sorry. We haven't included graviton exchange. If we include graviton exchange, it'll also have to have the subleading soft symmetry. Yeah. Now, by the way, let me make an account here. The conformal invariance is only promised to us, the full Virasoro symmetry is only promised once we include gravity, right? Just conformal field theory quantum field theory amplitudes rewritten as celestial amplitudes aren't guaranteed to have the full conformal symmetry, and probably don't. However, if you take, say, a large N gauge theory coupled to gravity, you can take a large N limit where gravity decouples. And so at some leading order, you still will have to have the full conformal symmetry. Now, ultimately, you'll need gravity for the full conformal symmetry. We're talking about tree amplitudes here. And so I think we get it anyway, but ultimately you need for the full exact conformal symmetry. When we start talking about non-perturbative effects and so on, we better be talking about gravity.
Andy, sorry, question. In your OP, I perhaps missed it, but in your OP, the representations that ran, were they the same representations that you had for your external operators, or you needed to add more as well?
No, they were different. They were different representations. The external operators were, and why that should be so, what the complete basis is, we don't so that basis, yeah, that's a great question. So that basis, what Pistersky and Shao showed was that if you have a normalizable wave function, you can rewrite it as a convolution over things on the unitary principal series, that they were complete bases. But if you have a normalizable wave function, which falls off like 1 over omega, and you act on it with the Hamiltonian, it's no longer normalizable. So the normalizable bases aren't closed under the action of the translation group. And that's the symmetry we're trying to preserve. So we've known for a long time that we needed to be discussing other values of the conformal weights. Not which ones we've needed to be discussing, but we knew that other ones were going to come into the game. And indeed, the subleading soft symmetry, both for gravity and for gauge theory, Lowe's subleading soft theorem, it involves something which is off the unitary principal series. And so there seemed to be a particularly interesting set of operators which lie on the real axis. The soft particles are negative integers on the real axis, and the Goldstone bosons are the positive particles on the positive points on the real axis. Now, my understanding, and many people here know more about this than I do, that in Liouville theory, what was a complete set of states? There are macroscopic states and microscopic states, and they were complete in different sets and different contexts. And how you're supposed to think about all of that was a very complicated story which took decades to unravel. And we have some story like that. So we don't understand, and your questions are great because you've asked the questions about all the things that we want to understand but don't. So part of the reason for doing the conformal block expansion was to get some idea of which states are important. And so we ran into a different set of states. And that's some information for us to include. And we need to understand where to go with it.
Sorry, so but in particular, the 3-point, the Cijk, does that is that related to a 3-particle scattering amplitude in any sense or not?
Yeah. So in Yang-Mills theory, we know that in Yang-Mills theory, we know that that when you take the collinear expansion of asymptotic gluons, you get a third asymptotic gluon. And so we knew that the at leading order, at least, that's at leading order. At leading order in the singularity, in the collinear singularity, which is the same thing as leading order in the OPE, we knew that the OPE had to close on the unitary principal series. And the singular part of the OPE had to close on the singular part of the OPE we knew had to close on the unitary principal series, and it did. there is no reason that the subsingular part needs to close on the unitary principal series, because they will involve extra derivatives, which will translate into extra momenta, which will translate into different conformal weights. But we knew it had to work that way in Yang-Mills theory, and it did. For gravity, there aren't collinear singularities of the same form in the OPE. There's still an operator product expansion that you can define by looking at the collinear expansion. And it doesn't close on the unitary principal series. And that's related to the fact that Mellin transforms in pure gravity don't exist. You can still compute the leading non-zero term in the OPE expansion, and two gravitons on the principal series give you something off the principal series.
And so, in particular, has nothing to do, nothing obviously to do with the three graviton scattering amplitude.
Well, the three graviton scattering amplitude the three graviton scattering amplitude on the unitary principal series doesn't exist because it diverges. It does exist off the unitary principal series, and it may well have something to do with the OPE may well have something to do with the 3-point scattering amplitude. But 3-point scattering amplitudes for massless particles, even in momentum space, are very singular. And that is why, in this example, we did these things with a massive exchange, because those 3-point scattering amplitudes are very nice when you have one massive and two massless particles. They are just 1 over z minus w to the h12, 1 minus w minus u. You know, they're just exactly what you would expect. The 3-point amplitudes, when you Mellin transform them, look just like non-singular 3-point functions in a conformal field theory. And that is why we looked at this case too, so as not to simultaneously be dealing with the issues of singular 3-point amplitudes and massless theories and the conformal block expansion.
Thank you.
Sorry, Andy, one more question.
Yeah.
When you mentioned that requiring the action of translational, the momentum, it takes you off from the principal series. But the new operators that you are required to have, I heard that, maybe I misheard, but you said that they live on real axis only, or they could have imaginary part, the dimensions could have imaginary part.
Well, it's actually in this slide here. Can I zoom? Well, maybe you can see. Here's the 2-point function of the leading OPE for two gravitons. First of all, if you treat z and z bar as independent, it still has a pole in z. And there's a beta function with some interesting weights. And then you get a new graviton whose conformal weight is the sum of the conformal weights of the old graviton. So if you started out with 1 plus I lambda, you'll get 2 plus I lambda.
Okay.
But in general, other terms beyond this singularity expansion, you can get many other terms. And in particular, for two massless and two massive particles, you can get basically any particle. I think this is true. Somebody correct me if I'm wrong, but I believe that the Shao and Lam showed this formula for any conformal weight. So there's a 3-point scattering of any OPE for any conformal weight. And if we turn that into a scattering amplitude, by conformal invariance, it has to have the standard conformal field theory 3-point function form. And a subcase of this, in fact, we showed in an earlier paper with Pistersky, Shao, and myself for 3 massive particles with related weights.
Sorry, I'm a bit confused. So this formula for the OP coefficient, it's valid for any conformal dimension, external conformal dimensions, you're saying? I mean, usually in conformal field theory, one takes the point of view that one doesn't quite know the spectrum and one doesn't quite know the OP coefficients. And then the bootstrap program is about predicting them.
That's what's different about this. We know the spectrum. We know the spectrum.
The 3-point function.
And given that we know the spectrum, the 3-point function is largely determined by or the leading term in the 3-point function you'll understand a little better what I mean by that. The leading term in the 3-point function is largely determined just by the symmetries.
Okay. So what should be thought of as the independent dynamical data?
Sorry?
What should be thought of as independent dynamical data of this theory?
Okay, I'm about to tell you that, and we haven't proven this.
Okay.
But when you look at the 4-point scattering, I think that the dynamical data, when we look at the 4-point scattering, okay, I'm not going to write this in print, but I'll say it. I think that the dynamical data, we're going to see here that the 4-point function is characterized by poles at negative even integers in the complex plane, and the independent dynamical data is the residues of those poles. Okay, so so this paper is sort of written, and it should actually appear. One of my co-authors, you can guess who, doesn't get things in on time, and so a starting point here is that since we're talking about gravity, and this is how gravity and these this story fit together nicely. In gravity, we expect all amplitudes. It's kind of a lore that if you take S goes to infinity with T fixed, and of course, that amplitudes should die exponentially. And in particularly, we expect them to die roughly like the black hole entropy. And the reason for that is that if you look at the intermediate states, it varies, you make black holes. And if you're talking, these are exclusive amplitudes. So if you look at an exclusive amplitude, since the number of intermediate states is of order the black hole entropy, each amplitude itself better be small, die like the black hole entropy as S gets large, in order for the total thing to work out to be finite. So, but now let's look at how this thing, so the fact that it dies exponentially is a wonderful thing because it means there can't be any infrared divergences when you compute any Mellon amplitudes, which are integrals of power laws of energies over this thing. The exponential will kill any of that. And now I want to look at the power series expansion of this in the center of mass energy S. And that power series, these are coefficients in the Wilsonian, coefficients in some effective action. And let's talk about tree level for now. And these are things out of which Nima and friends construct what's called the EFT hedron. And they found some incredibly powerful positivity constraints, generalizing the usual ones that come from unitarity, on the relationships between not exactly the APs of Z's, but the expansions of the power series expansions of the APs of Z's in Z. Z we can think of as the thing which governs the Reggie expansion. It's also the coordinate on the celestial sphere. So when we look at the Mellon transform of these amplitudes, there's only one, since these things are well behaved in the UV, the only way you get divergences is in the IR. And since we're integrating it against an arbitrary power of S, so the Mellon transform reduces to something like this after you collapse all the delta functions, and you just get an S to the beta, where beta is the total conformal weight of all four particles. And the only way you can get a, we have S to the beta minus 1 plus 2p, and that diverges logarithmically, which leads to a pole in beta whenever beta is equal to 2p. So that's the only way you can get divergences at tree level where there are no logarithms in this expansion. This expansion will have logarithms in it when we go beyond tree level. So at tree level, the celestial amplitudes are meromorphic functions in beta. It's simpler than the momentum plane where you have branch cuts and so on, and there are poles at negative integers. And the residues of these poles are coefficients of the effective Lagrangian or the EFT hedron, which have rich positivity constraints. Now, what happens when we go to the quantum theory? Now, the UV behavior is still soft, so the divergences in this thing, we believe in the quantum theory, or I'm going to assume it, so the divergences all come from the IR. So weirdly, the theory is all being determined by measurements out in the, by stuff that goes on in the IR. And so the divergences come from there, and they're still going to be meromorphic, although because there can now be logs, you can have multiple poles at, that turns into multiple poles that can happen, but still only at negative integer beta. And those are the poles that, and you can show that those poles are related to higher dimension terms in the effective action. Now, if we look at exclusive amplitudes, to even define these things, we have to put in an infrared regulator. We don't need an UV regulator. We're assuming that quantum gravity is soft in the UV. But we know an incredible amount about the logs that appear from the infrared regulator. The soft theorem says that they exponentiate in this form. I'm doing just QED here, and the soft, there's something similar for gravity, where this coefficient is related to the cusp anomalous dimension is proportional to the log of the IR regulator. Now let's Mellon transform to this celestial sphere, and something very beautiful happens, which is that let's see, I can't see this on my screen. Let me, yeah. So the celestial amplitudes factorizes exactly into a soft part and a hard part, where the soft part is just a current algebra correlator on the celestial sphere, where the level of the current algebra has a IR divergence in it. At the same time, the dimensions, hence the word anomalous dimensions, the boost weights of all the hard particles are shifted by an amount proportional to their charge. So you get this exact current algebra correlation, which of course is familiar from current algebras and CFT. We know that when you, this soft thing, it does come from a current algebra. There's a current algebra in these celestial CFTs. And we know that whenever we have a current algebra in a conformal basis, things factorize, matrix elements factorize. And all the IR divergences are in the soft part here. And so if we compute, for example, ratios of amplitudes, this will cancel out. And in fact, you can show that if you look at the dressed amplitudes, which are required by charge large gauge charge conservations, these are canceled in there, and what's left is just the hard amplitude. So these hard amplitudes are the RR safe, or IR safe, maybe even all the IR safe information in the theory. And this also works for gravity, except for instead of Q here, we have that operator P, which shifts the conformal dimensions of the thing in the amplitude. So there's some possibility here that we have an IR finite S matrix, which is sorely needed in any studies of quantum field theory or quantum gravity if we want to make well-defined statements about symmetries. We need something for it to act on. If we want to know whether black hole information is unitarity, we can't throw out an infinite number of soft modes that are correlated, we know, with the hard modes. So there are lots of reasons that we want to, that this object might be useful. This is a partial answer to the question that Shiraz was asking earlier, and he looked like maybe he had another one there.
Yeah. Sorry, just a quick clarification. Does A hard obey A dagger is equal to 1?
So this is pretty new. There's some things about this we don't quite understand. I'm hoping that's true. We'd have to understand what dagger means and how you sew together A with A dagger. You know, there's a formal argument which is actually wrong. We've realized that Faddeev-Coolidge amplitudes are unitary because it's but there are various infinities floating around. And so I'm not going to claim that now, but I will say that I'm pursuing the possibility that A hard dagger is unitary. But if you want to, for example, look at something like the memory effect, that would be a ratio of these things. So a lot of things involve ratios.
Okay, thanks.
It will certainly be way more interesting if it turns out to be unitary on its own. So here's a question that people have been attacking from a surprisingly wide variety of views. There was just a long paper on it, which you're familiar with. What is the most general form of the graviton 4 amplitude consistent? And then everybody has their favorite symmetry that they're going to demand. And it looks like a fantastically over-constrained problem. Maybe we can solve it, and it would be really cool if it ends up looking somehow like string scattering. And so let me stop there. So the reformulation of Minkowski scattering as correlators on the celestial sphere is leading to new insight. A lot of stuff we don't understand. Thank you for listening.
Thank you very much, Andy, for a wonderful talk. Let's all unmute ourselves and thank Andy. Questions?
So
go ahead, Indramil.
hi. So I was asking you about computing the amplitude in the bulk, let's say semi-classically, and then checking if the commutator of the currents are as it is. And you said that you will probably say something at the end.
Okay, so I said something about the UV there. That's kind of what we understand about the UV. I think that these soft operators that we know that these soft operators that are generating these symmetries are related to these poles. They have conformal weights that lie on the poles. and so there's some connections there. But I can't, I can't, I don't really have more to say other than it's an interesting thing to try to get an angle on.
You know, why I was saying is that suppose, you know, these currents have this hard part, and that is roughly like integrated on a null direction. Let's say on the Cry plus, let's say it is integrated on. And if you have two operators of that sort separated on the sphere, now if you bring them close together, then there could be some UV properties which might show up.
Well, by the way, let me mention, because I forgot to say it, on taking these operators and integrating them on a null surface is weighted by something is in fact exactly what these light ray transforms are. There's a family of light ray transforms, and it's, I think the Mellon transforms are a special case of these light ray transforms, and that must have something to do with the fact that we're seeing these light ray transforms in this OPE decomposition in this conformal block expansion. Yeah, I mean, it's certainly interesting to see what happens, how these operators mix when they come near to each other, and that is what we're trying to get at with studying this OPE expansion. This OPE expansion, of course, it has an infinite, I think it has an infinite number of terms in it, which are less and less singular. And we only computed the most singular ones, and the less singular ones will depend in a way that we were able to quantify in that paper. They will depend, if you do the computation in a Wilsonian theory, they will depend on the coefficients of the Wilsonian effective action.
Okay. And it might also be sensitive to the UV properties because they are coming close together roughly. So,
what would be sensitive to the UV thing is what would be sensitive to the UV thing. Well, there's some sort of weird UV IR mixing here.
right, exactly. Yes.
And it's weird that you're getting UV IR mixing without putting in field theory, because as you take two operators closer and closer together, the less divergent terms on the celestial sphere come from the the terms in effective action, which are important in the UV. And you can do this computation for an arbitrary Wilsonian effective theory, but an arbitrary Wilsonian effective theory, almost none of them will have an expansion which converges and gives you something nice in the UV. So what's potentially powerful about this approach is the global existence of the Mellon amplitude, which we can presume from the soft UV behavior of quantum gravity, might be giving us a way to implement that constraint.
Okay, thank you. Yeah.
Any more questions?
Andy, when you did in let's say 4-point scattering, you had two particles coming from the past and two particles going to the future. And when you did your OPE expansion, were you taking the two particles from the past close to each other and the two future ones close to each other, or could you also take some cross?
That table had both, and they're different. They're different. Right, they're different, however, in a way that is consistent with the, those OPEs have poles in them. The coefficients of the OPEs have poles in them as a function of the conformal weights. And those poles all occur off the principal series, where at negative even integers, and they correspond to the soft theorems. And so there's a relationship between the incoming and the outgoing OPEs that's dictated by the soft theorems.
Okay, thank you.
The poles have to do the same thing, but the subleading terms don't need to, and they don't.
Okay, and does the same spectrum of operators run if you take two guys from the past together, or one from the past and one for the future?
Yeah, the spectrum of operators is just the spectrum of free states, but there is mixing. The OPE says that once you turn on interaction, the states mix. So I guess that means that there's some sort of non-trivial density of states as a function of conformal weight that we don't really, I don't know, I haven't thought about how to compute that.
Okay. Sorry, one more unrelated question, or marginally related question. You talked about these singularities that followed from translational invariance. And you talked about how there was some similarity between these and these bulk point singularities in ADS-CFT. Now, the bulk point singularities are approximate singularities. The singularities we see in supergravity, and if I remember right, they go away when you include alpha prime effects and go away when you include G-string effects. On the other hand, your singularities are exact singularities, right? They will survive all quantum corrections and so on. Is this right? And is this a difference?
Wait, is that right? I didn't know that. The bulk point singularity in any CFT, it disappears?
I believe so. I believe the artifacts of being at large n and large coupling. Somebody should correct me if that's wrong.
I think I've heard that. Yeah. Well, I guess it's a question of whether there's anything that would make the celestial sphere fuzzy. Is that the question? Yeah. Yeah, I can't think of what would make them go away, but there's no large n here yet. There should be some large n. There should be some way of putting there's no other parameter here yet. You know, when Brown and Hainaut did their analysis, they didn't have an n. Which was really needed to, you know, understand it. So we're still back in 1986. We haven't gotten to 1997.
Okay, but there's a loop.
What? You disappeared. You're somebody finally figured out how to mute Shiraz.
There's a loop expansion parameter in the bulk. There's no analog of alpha prime because we're in a infinitely big space, but there's an analog of G-string, right?
There's an analog of G-string, and it's certainly an interesting thing which I hope to pursue to understand, you know, how the string theory amplitudes, what there's more properties of their celestial transform. There's some beautiful papers by Stieberger and Taylor on this, but there's a lot more to be understood. Yeah, I don't know.
Yeah, I don't quite see the loop expansion doing that. I mean, the translation variance seems to be an exact symmetry. So, yeah. Of course, but maybe that's part of the point, is that the states in the conformal basis are not exactly, they're not translation eigenstates. Right, so if they're not translation eigenstates, it's, they wouldn't necessarily need to have this delta function singularity. Yeah, I don't have a good answer, Shiraz.
Thank you.
Sorry, I was going to ask perhaps a related question, that this delta function singularity of the 4-point function seems to be a kinematical artifact, just a translational symmetry. Then is it possible to impose translational symmetry at the level of the conformed blocks themselves, so that the blocks themselves have delta function singularities? So you repackage a whole bunch of blocks into something that has translational whatever covariance.
Right. We've been trying to understand what I mean. You have SL2C blocks, and then you enlarge them to Virasoro blocks. They combine it together into Virasoro blocks. Maybe there's something called a Poincaré block. I'm not sure exactly how you would define it, but there should be some sense in which those expressions involve those combinations that appear there. They're very special combinations that they are somehow Poincaré blocks. But the most we've been able to do in this subject is to coin the catchy word Poincaré block.
Any more questions?
I actually have another Zoom at 11. So
Okay. So let's thank Andy for again for
really
a
great
really
to see
wonderful talk.
everybody. I'm sorry we don't get to go for Indian food and go for a little walk out on the ocean out there.
It's great to see you, Andy.
Great to see you. Great to see you. Bye-bye.
Thank you very much for doing this.